Next session is an English session. Speaker is from the top tier Python company, INSTACRAM. Everyone knows like Instagram is probably the biggest Django app. So the topic is about the journey of async adoption in Instagram. Let's welcome the speaker, Jimmy LIHE.
Hi. Today's topic is about how we use ASYNC in Instagram backend. So we will talk about what's ASYNC, given some introduction, and then starting talking about how we use it, and then we will have some minutes for Q&A. About me, I'm Jimmy LIHE. I'm a software engineer in Instagram infrastructure. I like Python a lot. I have been joined many PyCon Taiwan and PyCon US. My recent interest is in Python efficiency. So try to figure out how to write more efficient Python code and use some profiling technology to identify the bottleneck. And then for CPU bottleneck, we can use Python to optimize it. And for latency bottleneck, we use ASYNC to optimize it. So I'm in efficiency and reliability team in Instagram. Our Instagram user growth is very fast, and we also keep developing a lot of new features. So our number of servers also grows very fast. So that's why we have a dedicated team to work on the efficiency, try to slow down the number of server growth. So let's take a look at the Instagram backend architecture. So we run Python Django application. So when the server starts, it will start in the USG process. So there will be a USG master process start loading the Django application to memory. And after that, it will do fork to multi-processes. So that's our web server. And so when we serve in a request, we need to fetch a lot of data from different backends. We use memory cache, Cassandra, and many different Swift services to fetch the data, do the ranking for our media, etc. And before we started using ASYNC all the I/O are in blocking mode because in Python to Django application, the I/O is blocking. That means when the process is waiting for I/O, the CPU will be idle. And to keep the overall system busy, we try to run more number of processes than the number of CPU. So in this use case, you can see we have 3 CPU core, and we try to run 6 processes of the USG Django application to keep the system busy. All the processes share some memory because they are forked, and each one also have some private memory page. So then what's the problem of blocking I/O? So blocking I/O will make our API respond slower because all the I/O needs to run in sequentially. And when the API is slow, the user will have a bad experience. And in the meantime, to keep the CPU busy, we run a lot of processes. That means the operating system needs to do context switch between processes, and the overhead is high. And if one of the requests for some reason is pending for a long time, so in USG there's a hierarchy mechanism. So you can preset a hard limit on the latency, let's say 10 seconds. And when the request didn't respond in 10 seconds, the master USG process will send a terminate signal to kill it. And after we kill that, we need to restart the process. And this is also has high overhead. So those are the problems we try to solve using async I/O. So what's async I/O? Async I/O is asynchronous I/O. So it enables us to run I/O concurrently. So in traditional blocking I/O mode, our application will do some CPU work, and then I/O work, and then some other CPU and I/O work. I/O will usually take much longer time than CPU because you need to send the data over clusters and data center. So then in async I/O mode, we can run the I/O concurrently. So that means while we are waiting for the first I/O, the CPU can working on something else until we reach the next I/O, and we can run the I/O concurrently with the other I/O, and CPU can continue to working on something else. So it's just like the chess simultaneous exhibition. So simultaneous exhibition means a expert player, chess player, play the chess game with multiple non-expert players. So in this graph, the children, he's an expert. He can come out the next step in a few seconds. However, the adult player, they are not experts, so they need a few minutes to come out to figure out the next step. And so the child can just go to the next player and play the next step, and then to the next. So that means everyone will be busy. So the child is just like CPU. It always can find something to do. And the non-expert adults, they are just like I/O. They need more time to figure out the next step, but everyone is busy. So with the async I/O, we expect it can make our API running faster, and our user can get better experience. And in async I/O, we are doing in-thread context switch. The overhead should be less than process context switch. And for hierarchy problem, if we run multiple requests in the same thread using async I/O, when one of the threads is pending for a very long time, we can simply ignore it. It won't block other requests, and we can even just cancel the async task without kill the process. So it also can help us reduce some overhead. And let's talk more about some misunderstanding about async I/O. So first, async I/O is not multi-process. It's also not parallel computing. It's single-threaded. That means at any given moment, only one function can be executed. Only the I/O can run in concurrently in async I/O mode. And second means async I/O is not always faster regarding CPU and latency. Because for CPU, async I/O has the overhead of event loop. Event loop needs to do context switch between different async functions. So there will be CPU overhead. So it usually will use more CPU. And for latency, simply converting your blocking I/O to async I/O won't come with latency win. You need to restructure your code to explicitly specify which I/O can run concurrently to get the latency win. So let's start with async syntax. So starting in Python 3.5, you can use async and await syntax. You use async define to define an async function. And inside the async function, you can await another async function call. In this example, sleep and return is an async function. It will asynchronously sleep for a few seconds, depending on the input. And after that, it returns the second value. So after you convert a function to become an async function, if you just call it, it will return immediately. The function is not running yet. It's returning a coroutine object. Coroutine object is a execution container for your async function. So with this container, the event loop can decide when to start your async function. And so remember to use await if you want to run your async function. But you can only use await in async scope. That means inside async defined function. So if you want to run a async function in a non-async scope, then you need to start the event loop. So you can do async IO event loop and run until complete with your async function call. Then you will run your async function and return a result. In order to get the latency win, you need to do async IO gather. Gather can given some async functions. Those async functions will be running concurrently for their IO. So in this example, we run sleep and return for 1 second, 1 second, and 2 seconds. And so if they are running concurrently, then it should take 2 seconds instead of 4 seconds when we want them sequentially. So we use given loop run till complete to run it. And in the end, you can see it finish with 2 seconds. So it's running asynchronously. So gather is the key to get the latency win. In order to get more latency win, you need to use more gather. And how async IO works? So we know we start the event loop by calling run until complete. So run until complete will given a coroutine or future object, and then it will start a infinite loop, run forever. And in the infinite loop, it will run once for each round. So in run once, what we want to achieve is we want to figure out which IO is ready, and then we want to continue to run that IO ready async function. So in order to make this happen, we need to make sure the IO is in non-blocking mode. So in Python, take socket as example. You can set blocking as false. Then after you do that, if you call socket send or socket receive, it will return immediately. Then we need a way to get notification when the IO is ready. So what we can do is we can use the epoch selector. We can register the IO to the selector, tell it what's the file descriptor of the socket and what's the event we want to listen. And when the event is ready, when we call select, it will just return the event ready event. So if we're looking into an example, this async function in the event loop, async socket receive. So this function is for receive n byte of data from a socket. So it's an async function. So what it did is it created a future. Future is a container for async function. It keeps the data and status of the async function. And then it try to get the file descriptor of the socket, and then it wrap the future. It wrap the callback function in a handle container. So handle is a container for event loop. It just for keeping for storing the callback function. So this callback function is the function we want to call when the IO is ready. And then we call register. We tell operating system that we want to listen to this socket file descriptor. Whenever it's ready for read, the event read, please tell us, and then we also provide the handle, which is the callback function, as argument. So, and then when you run all those, all the steps are non-blocking, and then it will block on this statement, await future, because await will realize future is a not finished future. So when it will go back to the event loop. So that means it will go to the run once, and run once will select, And this select will be blocking until any of the registered file descriptor is ready. And then we will get back the event list. And in the event list, it has the file descriptor and the callback function handle. So we call process event, and then we add the process event will add the handle to a queue ready. And then here we just try to run the handle, try to call the callback function. And the callback function underscore socket receive is just try to read the data because we know now the data is ready. So that's how ASYNC works. And as you can see, there's some back and forth from your async function to the event loop, from event loop to another async function if you have gather. So there's some overhead in this area. Okay, so now we understand how ASYNC works, then we can start to think about how we want to use ASYNC in Instagram. So adopting ASYNC in Instagram is just like we have a very big forest. You can imagine in this forest a lot of trees. Each tree is just like a call stack in our Python repository. And what we want to do is we want to identify some of the tree, not all of the tree, and we want to decorate them. We want to migrate some blocking code to async, and also move the stack to become async. And it's hard because Instagram started back to 2010, so it's already developing for a while. And in our repository, we have a lot of code, and a lot of developers continue to updating the code. So we will have the following challenges. First is scale. How do we collaborate with a lot of product developers to gradually moving from blocking I/O to async I/O? And we also need to provide some utility to make async I/O more easier to use, and also make sure moving to async I/O won't cause any application failure. So we also have bug fix. And because of too much work to do, so we also figure out a way to prioritize our work. We have blocking call finder for this. And a lot of the change is repeated, so we also do some automation. And in the end, we also want to make sure the async I/O is CPU efficient enough. So the first thing we need to do is we need to have all the backend clients has async I/O support. We mentioned we use Thrift. So for Thrift, we have open source FB Thrift. You can compile a async I/O supported Python client by using Py3 or py.asyncio namespace. Py3 is based on Python, so the generated code is more efficient. And we also use HTTP using request library, but request doesn't support async I/O, so we use ARHTTP to replace it. And for other common backends like MySQL or Cassandra, you can find the async supported client in this GitHub account, AIO libs. And after that, we want to provide some libraries and helper functions to make async I/O easier to use. So as we saw, every time you want to run an async function, you need to call async IO.getEvent loop that run till complete. It's not simple enough. So we add a wrapper, wait for. You simply call wait for with your async function. So you use this in non-async scope to start your async function. And for testing, unit test framework doesn't support async test function. If you just make your test function become async function, it doesn't run because the framework will just call your function and it return coroutine immediately without running it. So we add a helper. It's a decorator async test, and it's simply calling wait for the async test function. So with those helpers, we can write async code easier. And then about stack migration. So what we want to do for async migration is we want to identify the blocking backend library call, for example, blocking thread call, and then we want to change to use the async version, the async thread call, and we also need to migrate the caller func to become async function. So in the call stack, we are doing bottom-up approach because the I/O always happen at the bottom level. So we identify the bottom level blocking call and we make it become async call, and then also moving the async stack up. And eventually, when we find a parent which call 2 or more async function, and if those async functions are independent, then we can gather them to make it running concurrently. And in order to identify blocking call, we build a tool, blocking call finder. It's because our code base is really big, we want to have a good way to prioritize our work. So what we try to do is, given this function call stack, F call blocking thrift, and G call H call blocking HTTP call. Given this, we want to represent it in a tree-like visualization like this. So here we can clearly see that the top level function is the API entry point. And we can see there are 2 stacks have blocking call. And then one of them is shorter, 2 level. It's easier to migrate. And so we want to prioritize it based on the easiness and also the importance. So in this case, you can see we also try to collect the latency in production and also number of call. So that means API call F 50K times, and the average latency is 20 milliseconds. Compared to the another stack, it's only 10 milliseconds and has fewer calls. So we should working on the API F stack first. And the way we implement this blocking call finder is we build the provider to collect the stack trace at runtime, and then we use the PyGraph to render the graph view. So with this, we can easily identify the action items. And then sometimes the function you want to migrate to async has a lot of dependency. Let's say we want to migrate this non-async function to become async. You can see this one has a lot of different callers. And when you migrate a function to become async, you need to change if the function has async caller needs to await the new async function. And non-async caller needs to use wait for helper. So if the target function has a lot of caller, then your change set would be too big, and it will be hard to for code review and commit. So in this case, we provide a helper to help us minimize the changes. So it's the sync wrapper. So sync is a function you provide a async function name and then assign the return to the original non-async function. So that means we identify a function func and we want to make it async. So we make it become an async function, and then but we also rename it to become async func, and then we add this line at the end. So so for all the callers, for the caller we want to migrate in this change set, we can simply call in the async version. And for the non-async caller, we don't need to change it. They can still call func, and it will just work. So what sync does is it's basically trying to call wait for when you call the func. But there are some cases to handle. For example, if your function, async function is a class method, it's a static method, then you need to handle it slightly differently. But by doing that, we can prevent to keep two versions of the same function. So we don't need to keep async and non-async version. We can simply change this function to become async and then add this sync wrapper. And during the journey, we also identify some issues, some exception. The first one is the runtime error. This event loop is already running. So if you have a stack like this, you call run until complete and async function. Async function can directly call non-async function, and eventually you want to call another async function, you need to run another run till complete. When you run this second run till complete, you will get a exception, runtime error. It's because the event loop is already waiting for the async f function. So it doesn't allow you to start the loop again to waiting for another async call. So our fix for this problem is when this happens, we will just create a new event loop and then running the async I function in the new event loop. Ideally, we should just simply make the entire stack async and make everything running in the same event loop. But our code base is big and stack is very complex, so it's inevitable that sometimes we do need to have this happen temporarily. So we add this helper. So it's still wait for, but in the wait for, we do need to check whether the loop is running. So if the loop is not running, then we return the current loop. If it's running, then we need to get a new loop. And to make it more efficient, we have a loop pool to reuse the event loop. And the other exception we saw is another runtime error. Event loop stopped before future complete. It's a very tricky bug. It took us quite some time to figure out. So what happened is in our application, we will call run until complete a lot of times because we are still in the middle of the migration process. So if your top level stack is not async, and then you need to call async function in different stack, you will call run until complete multiple times. And what happened is in some previous run until complete call, there's some orphan future left over in the loop, and it will also be executed in this run until complete run. And when those orphan future they finish earlier, their callback function will try to close the loop, and the event loop will check if the loop was closed, but the future it's waiting for is not finished, then it will raise this exception. And this happened is because in the earlier round of run till complete, the future actually raise an exception when it's running. And as you can see, this is the patch I submitted to fix it. So before that, if there's an exception, it will just raise. It won't clean up the callback function. The callback function will close the loop, stop the loop when the future is finished. So the fix is simply move this statement to a finally section, then we can make sure even the loop was interrupted by exception, it can still return gracefully. And another common issue is global variable issue. So the issue is because the execution order of your async function is not guaranteed. It depends on the I/O networking situation. If one of them I/O return faster, then it will continue running. So if you have a example like this, you run function called gather f and g, and f is trying to read and write value from database 1. It's writing to a global variable var value. And G is doing the similar thing, but it's trying to read in and write in from another database. So what happened is the execution order could be random, and it could become like the first read and second read finish in sequential, and then it starts the write of G function first, and then you will get the wrong. So if the f write to DB function finish after start after the read from database 2, then it will get the wrong value. So in order to solve this problem, we need a context-aware variable. So in Python 3.7, there's a context vars. So with context vars, you can just create a global variable. And whenever you do gather, it will automatically copy the parent context variable and create a new context in your async function. So in this case, you can make sure the value you write and you read from in a different async function would be consistent. And in order to get more latency win, we also try to achieve the more concurrency by adding more gather. And we have a awaitable design pattern to make it the concurrency. So this is an example: run will await on F, and in some condition it await on G and H. It awaits on G if condition A is true, await on H if condition B is true. So in this case, if all of them should be run, we want to run them concurrently, F, G, and H concurrently. So the way we do it is we prepare a list of awaitable. We prepare the awaitable F, G, H. If A is true, we will call G. But if it's not true, then we use a helper identity. Identity is a async function. You given a value, and then you will just return the value when it's awaited. So here we simply provide the default value none. So by doing this, we can make sure if FGH, if they need to run, they will always running concurrently. And we also use LINT to provide guidance to our developer to write better async IO code. So we have some rules. The first one is about we actually have a naming convention for our async function. So we want to have async underscore as prefix for all the async function. It's because it's easy to forget to await an async function. So having this convention can remind the developer that you are calling an async function, you should await it to get the value. And the second is gather await in loop. So let's say you have a for loop and you do await. So those await will become sequential await. We can actually gather them. So when this happens, we provide a warning in LINT. And the third example is warning when people are adding new blocking call. we want to move in everything to async. But before we move everything to async, we cannot remove the blocking call library, so we just add this warning in LINT. And we implement those LINT using AST and FlakeGate plugins. So for the automation part, so you can see many of the work is simply changing the syntax from async to from non-async to async and add a wait. So for those easy change, we want to automate the process. So then we try to build a smart call modifier. So what we need to do is, first we need to, whenever we decide to change function, we need to figure out the callers of this function. So we collect the caller callee data from runtime profiling, and we also use offline static analysis. So then given any function, we know what's the callers. And then with all the caller callee database, we can identify which function has blocking call. And then so then we can build a call modifier for it. So our code modifier is based on AST. So we compile the source code, become an AST tree, and we modify the tree. So the modifier will modify the tree. And then we use Aster, open source library, to convert the AST to source code. And then we create a pull request and waiting for code review. And after that, we can submit it. And for code modifier, we do the automatically code formatting using isort and block library. And the last issue is the CPU overhead, and this is a very important one. So we do a lot of optimization to async IO while we are using it. If we do nothing, it will take about 20% of the CPU instruction in our Django tier. And we look into why the overhead is that high. And in the end, we identified it's slow because most of the async IO implementation is implemented in Python. So what happened is in C Python, many of the libraries implement in Python, not in C. Python is more readable, but it has the efficiency problem, so including the implementation including event loop and helper. So we need to optimize it. And the way to optimize it is we can simplify the logic and remove some redundant computation to use more efficient data structure to make it faster. And we can also use Python to add in C type to the code and compile the code to C, and it will also be faster. And the last one is implement the function in Python C API, and it will become very fast. So when we're working on the optimization, we take a look at the existing optimization from open source first. So for the UV loop efficiency, there's a UV loop library. So it's a replacement of the built-in async IO event loop. You can just import UV loop to replace it. And the underlying is calling libUV, which is the Node.js event loop implemented in C, which is much more efficient. So we use this. We saved some CPU. And we also apply some optimization in 3.6 and 3.7 Python. So some of the critical common data structure, container, and helper function are implemented C in those versions, including future, task, and get event loop function. So with all those, we also have our customized optimization. For example, we've identified gather is also expensive for us. So we take a look and we find gather called ensure future. Ensure future call its future, its coroutine is available to check. And so our first optimization is we reorder this check, because usually we will gather async call which is providing the coroutine. So we should check its coroutine. Then we don't need to check its future. Then it return earlier and it's faster. And we also remove an assumption that gather assume you could provide duplicated coroutine and it do the dedupe using a dict. And we also implement some of the helper function in C API to make it faster. So in the end, our current status, we make it 2 times faster. So it's costing 10% now. And we are still working on it. So the current result of our async adoption is we continue to move into async IO, and many of our major API already have more than 30% latency win on server side. And we do see user engagement improved. Users are trying to see more media, photos, stories with shorter latency. And they also have longer time spent on our application. And our next step is to continue the work to move into 100% async. And in the meantime, we also build in the concurrent request handling to handle multiple concurrent HTTP requests in the same thread. So now it's time for Q&A. And so if you have any question you couldn't make it today, you can write me email, jimmylight@instagram.com. And if you have any question about the life in Instagram, or you want to find a job, you can also contact me. And here I have 2 small gifts for the first 2 questions. So any question?
Any question? Nope.
Okay.
Hi. I would like to ask if you have considered other async libraries like Curio, CURIO, or Trio before you start using async IO. Thank you.
So before we move into Python 3, we are using TrueLayers, and it's a backport of async IO module for Python 2.7. We didn't consider Curio. We are not sure if it's mature enough. Yeah.
Okay. Any question?
Okay.
Hi, I have a question is about Django is a synchronized, and how you write a synchronized code in Django. Thank you.
Yeah, that's a good question. So the question is how you write asynchronous code in Django. So it's true that Django has the request handler and middleware and the views. All of them are not async function. So in order to using async IO in the Django code. So what we did is we actually we have a copy of Django and we are updating it. We make all the stack in Django become async, including some of the feature in Django we used, like signal receiver. So after we make those stack become async, we can do async IO. Any more questions?
I think I can ask one. So
Yes.
as far as I know, Instagram also work on Python 2 to 3 migration.
Yes.
This few recently, right? So how do you have any coherency between your async migration and the Python 2 to 3 migration?
Comparison of
not comparison, like how the company first migrate from 2 to 3 and later migrate from non-async to async.
Yeah.
The schedule, how company
I see.
handle that.
Okay,
Yeah.
so the question is about how what's the schedule of migrating from Python 2 to 3, and then the schedule about ASYNC migration. So the Python 2 to 3 comes earlier. So we spend almost a year to just make Python 2 to 3 happen, and it's finished early last year. But during the migration, we already have people working on investigating the async IO, and at that time we're still in Python 2.7, so we are using the Trulius, the backport of async IO module. And after we moved to Python 3 last maybe February, we starting adopting more async IO more aggressively.
I see. Okay, so time's up, and thanks for the speaker from Instagram. And for the people who has QA, please come to the speaker to get a gift. And thank you. That's all.